Alright, so we're going to transition from talking about Newton's second law problems to setting up setting up our work and energy problems. And so for starters, let's just start with definitions. So one definition that we have for energy is that it's the ability to do work. Of course, when we talk about work, we tend to define it as the transfer of energy. So what you notice is that basically we've got a situation here where we've got a nice little circular argument going on. So what we're going to do is we're basically going to say, you know what, one of these things is simply a fundamental concept that we're not going to have a really good definition for, and for us, that's going to be energy. So basically the way that we're going to deal with work and energy is we're going to say we don't have a very good definition for energy. But once we've established that, we do not have a very good definition for work. Work is going to be a way to transfer energy, and we'll come back and talk about the particular type of energy transfer that we'll start dealing with. And so what do we do with energy then? Well, first off, we're going to learn to recognize forms of energy. So we're going to have these different forms of energy that have different names. We're going to focus mostly on the first two, so kinetic energy and potential energy. But in other classes that you have, you may end up talking about chemical energy. You may end up talking about, in 299, you'll talk about electromagnetic energy. In 299, you might also end up talking about nuclear energy. So there are multiple forms of energy, and the first thing that we do is we end up learning to recognize those forms. The next thing that we end up doing is we learn how to keep track of the amount of energy. And the nice thing is that we're going to see that energy ends up working a lot like money. Basically what we're going to have is we're going to have accounts of energy, and then we're going to be able to transfer energy back and forth between those accounts. So in some sense, what the work energy theorem is going to allow us to do is it's going to allow us to keep track. This is our bookkeeping device with energy. And so if you transfer some energy from kinetic to potential, we're going to use the work energy theorem to keep track of that. And then the other thing that we need to recognize is that work and energy are scalars. They're not vectors, which makes the problem a lot simpler in a lot of ways. So we tend to like working scalar problems. All right, so we said work is a transfer of energy, and in particular it's a transfer of energy due to an action of a force over some distance. So in general, we define the work this way. So the work is defined as the integral from some initial position to some final position of the dot product of some force in with these tiny little steps, infinitesimal steps of displacement in going from where you started to where you finished up. So a couple of things to sort of keep in mind about this. One is work involves a dot product. Dot products, as we'll talk about in class on Wednesday, are basically how we're going to convert vectors into scalars. So a dot product ends up being just a scalar thing, which is why work is just a scalar quantity. The contribution to the work over each tiny little step, well, it can be positive, it can be negative, or it can be zero. So it'll be positive when the force and our tiny little step dr project in the same direction. Basically what this means is that so if here's my force and here's my infinitesimal little step, notice that the force has a component that points in the same direction as my tiny little step. There it is. So this is a case where the component of my force parallel to the displacement and the infinitesimal displacement point in the same direction. The work done by a force will be negative when that force and the little infinitesimal displacement project in opposite directions. So again, here's my force, but now when I break it up into the component, or think about the component of this force that's parallel to my infinitesimal displacement, they now point in opposite directions. So pointing in opposite directions means negative work. And then zero, right? Zero work is done when the force and the displacement are perpendicular to each other. So this force does zero work for this infinitesimal little displacement. So, and then the last thing that we want to keep in mind is that in the same way that a force is an interaction between two objects, well, we need to keep track of, or label is really probably the better word, when we're talking about the work on what by what. And we'll see that one of the things that can be very confusing is that you can talk about the work done on a particular object by multiple forces, and so we just want to keep track of everything as we're going through the problem. So this is, again, in some sense, this labeling and being clear about our label is another part of the bookkeeping. All right, so if in the special case where we've got work done by a constant force, so we've got a constant force that pushes on an object to move it through some displacement, then what we get is we get a simplified version here. So again, if the force is constant, there's going to be some, so our dot product reduces down to just thinking about this cosine theta. The force being constant pulls out of the integral. So I'm just left with an integral of my tiny little steps dr, and that ends up just being the displacement. So one way that we can calculate the work is to say, well, the work done by a constant force is just going to be the magnitude of the constant force F times the magnitude of the displacement times the cosine of the angle between them. So here's a situation where, let's say there's my force F, and it's going to move this object through some displacement r. Then again, I can now think about, there's the force, there's the displacement, and then here is the angle theta, the angle between those two vectors. So again, what this tells me about is that I really only care about the component of the force that is parallel to the displacement. So when I think about this force vector, right, I can break it up into a component that's parallel to the displacement and a component that's perpendicular to the displacement. And what I see is the component that's parallel to the displacement is the only one that does work, because that component is the one that's given by F cosine theta. This is my F sine theta component, and it doesn't do any work here. So it's only the parallel component that does work, and it'll do positive work if it points in the same direction, negative work if it points in the opposite direction. The perpendicular component of the force doesn't do any work, which is why if the entire force is perpendicular to displacement, then there's no work done at all. So if we've got multiple forces acting on the box as it moves, so here we've got force 1, force 2, and force 3, and again we're going to let this box move through some displacement, so these are all constant forces. Here's my displacement, so again I can think about them relative to the displacement. I just need to do it 3 times. So what I'm going to be able to do is I'm going to be able to calculate 3 different work terms, one for the work done by force 1. So again, this is part of my labeling. You'll notice that the displacement for all these is the same, but the work done by force 1 cares about the magnitude of force 1 and the angle between force 1 and the displacement. So here's my angle theta 1 right here. Since theta is an angle between 0 and 90 degrees, that means that the cosine of theta is going to be a positive number, and so the work done by force 1 on my object will be positive. Force 2 will also do work, but you notice that force 2 happens to be perpendicular to the displacement. So here's a situation where to calculate the work done by force 2, I need the magnitude of force 2 times the magnitude of the displacement times the cosine of the angle between force 2 and the displacement. And in this case, theta 2, that angle, happens to be 90 degrees. Since cosine of 90 degrees is 0, the work done by force 2 is 0. And then the last one is force 3. So again here, what I'm interested in, the work done by force 3 on the object is going to be the magnitude of force 3 times the displacement times the cosine of the angle between the displacement and force 3. Here, that angle between the displacement and force 3 happens to be 180 degrees. Cosine of 180 degrees is -1, so the work done by force 3 will be negative. That's certainly true since force 1 points opposite the displacement, but it would have been true for any force that points that has an angle that's larger than 90 degrees. So from 90 degrees to 180, the cosine of any of those angles is negative, and so the work done by all of those, any force, over here in the second quadrant would have been negative. All right, so just to kind of summarize what we should take away from this. One is that forces do positive work on an object if they have a component that points in the same direction as the displacement. That's a situation where the angle is between 0 and 90 degrees, so the cosine of that angle is going to be a positive number and the work will be positive. Or, second option, forces do negative work on an object if they have a component that points in the opposite direction as the displacement. So for angles between the force and the displacement that are greater than 90 degrees all the way up to 180, the cosine of any of those angles will be negative, and so the work will be negative. And then the last one is that if the angle happens to be at 90 degrees, then the force does 0 work on the object. So forces that are perpendicular to the displacement do no work. And so this is what we'll start thinking about calculating the force done by individual, or the work done by individual forces, is how we'll end up building up the work energy theorem, which is what our main bookkeeping device for keeping track of energy is going to be.